We're going to talk about systems some more, specifically stability of systems. And this will be a two-part series. And in the first part, I'm going to go back over some of the basics of systems that we started at the beginning of the semester, but talk about some things in more detail, fill in some holes. So it's going to be a bit of a review, but also we're going to get a couple missing pieces that will help for part two, and we're going to take a deeper dive into this question of how do we think about what is stable in a system, and how what's going on with these systems where we've seen, for example, if you think back to the lab on Daisy World, the Daisy World was stable for a while, and then it went out, and then it switched from a negative feedback to a positive. Like what was going on? What was happening there? So this lecture today corresponds to a reading. It's the first part of chapter 2 from the Kump book, and just a few pages. So this is going to be a relatively short lecture. Okay, so let's just start with defining what we mean by system, maybe slightly differently than before, but just to be clear. So this is a system is an entity composed of interrelated parts. I think it's interesting to come back to these definitions after we've been working with the material for a while, just to kind of take it to a little bit of a deeper level. So, entity composed of interrelated parts that function as a whole. And the parts of a system are connected, and we're going to call those connections couplings. So coupling is the links or connections between parts. And so this is like when we were drawing earlier when we were drawing the feedback loops, when we said, okay, A happens and that causes something to happen with B, and it's a positive or negative. That is a coupling. Okay, so couplings together describe feedbacks. So couplings can be positive, and that what we mean by that is if a change in one part occurs that causes change in the same direction, and I'm going to be a little more specific about that than I was previously, causes change in the same direction for the other part. Okay, so a way to think about that is a graph, right? So if we have A versus B, the positive the coupling has a positive slope on the graph. So if A increases, B increases. And if A decreases, B decreases, right? So negative is the same thing, so I don't, let's not write all that out, except this word is going to be opposite. Okay, So the negative coupling is going to have a negative slope. And we could even think about it a little deeper. The couplings, these links can be stronger or weaker, right? So that would be the equivalent of having a steeper or a shallower slope. So feedback, using this language, is a round trip of couplings. In other words, we start somewhere, it has an effect on something, and one way or the other, maybe there's something else that has an effect on, but we end up back where we started. Okay, so that's what a feedback is. And feedback is a self-perpetuating mechanism of change or response. So if it's a runaway, if it's a positive feedback, keeps going, at least for a while, right? A changes, things happen, A changes some more, things happen, A changes some more, etc. Okay, so the reading had an example of feedbacks that was just too good for me to not include, and I think it's a good opportunity to just to refresh on these, and also to maybe just take some delight in a great example of positive and negative feedbacks. Okay, so this is a true story about the former president Jimmy Carter and his wife. And what was written in his book was that, quote, during increasingly cold winter nights, the Carters argued about the temperature of the electric blanket. So they were in bed together and they each had a section of the blanket. Whenever I said it was too warm, Rosalind said it was too cold, and vice versa. And what eventually they discovered was that the controls for the electric blanket, so the electric blankets, if you haven't used one before, you can adjust the temperature. They'd been switched so that they were actually controlling each other's blanket. So what I want to start here with is how an electric blanket works when things are working properly. Okay, so when things are working properly, we have let's start with, so person A's temperature, their body temperature, I'll abbreviate that T, and we have person A's blanket temperature. Okay. So there's some relationship here, right? And pause the video for a second and see if you can put the label this with the pluses or minuses, one for each arrow, and then the one in the middle, just as a review. Okay, so if person A is feeling hot, if their temperature is high, they're going to want to cool down. So they're going to want to adjust the blanket temperature to be cooler. So when when A goes up, or when the body temperature goes up, the blanket temperature goes down. So that's a negative. If we made a plot of those two things, it would have a negative slope. And okay, so then if the blanket temperature goes down, person A's body temperature is going to go down too, right? Or if person A's blanket temperature went up, then their temperature was going to go up, okay? So that would be, sorry, that's a positive. Okay, so overall, this is a -1 times a +1. We have a negative feedback, or a stabilizing feedback. So that's how it's supposed to work. Okay, and that will allow the person to get comfortable and fall asleep and stay relatively comfortable throughout the night. Okay, so this is when, let's just say working. This is when working properly. Oops. Okay, so this situation that I described was where the wires were crossed. We had person A's temperature. So I'm going to refer to body temperature. And we have person A's blanket temperature. And we have another person. We have person B's it's going to work better if I put blanket temperature here. You know, I thought it would work either way. And then we have person B's body temperature. Okay, so we're going to draw, see if you can, again, pause the video, see if you can draw the sequence of arrows with pluses and minuses and determine what the overall sign of this, this feedback loop is here. If person A's blanket gets hot, then person A's body will get hot. Right? That's the same as up here. So this is a positive. Okay. But then we were told that the lines are crossed. So when person A gets hot, they turn down the temperature, so that it's a negative, but they're turning down the temperature on the wrong blanket, right? So it's the same as here. As person A gets hot, so their temperature goes up, then they turn the electricity down. So it's negative, but it's pointing at the wrong place, okay? So they're hot. Is it their blanket's hot? They get hot. They turn down the temperature, but it's on blanket B. So when blanket B gets cold, person B gets cold. So that's a positive again. And so when person B their temperature is low, they try to do the opposite. They try to increase the temperature. So that's negative, because those are the opposite directions, right? So like this is this relationship here. So this is the temperature of person B, and this is the blanket temperature of person A, right? So it's I wrote a negative, so it's going to look like this. So we said if person B has a low temperature over here, then they're gonna turn up the temperature in the blanket. So this is low and that's high. So you're up here, and vice versa. If they were really hot, they would turn the blanket temperature down, right? So we get this negative slope. That's what the negative sign means there. So overall, it's getting hotter and hotter for person A, and it's getting colder and colder for person B. So that is, and it's a runaway. It's not stabilizing, and we can see that if we multiply the +1, +1, -1, -1 all together as a positive. The book does a nice job of explaining this if that wasn't super clear. So hopefully these examples here, you've had an abundance of opportunities with these, also with these little graphs, to be super clear about how to label these, the pluses and the minuses. I noticed in the test that a lot of you were still mixing those up. So I'd suggest, if this wasn't clear, check out the reading and practice. Okay, so that's some review and some maybe a little bit fun. But the main topic here is stability. So to get a little deeper there, we're going to start by talking about, we're going to continue by talking about equilibrium and what we mean by equilibrium, or an equilibrium state. Okay, so an equilibrium state is occurs when the system won't change unless it's disturbed. And equilibriums can be what we call stable. And by stable, we mean that the system returns to equilibrium following a disturbance. An equilibrium state can also be unstable, although these are less common. But this would be a system that does not return to equilibrium. And there's a nice way of thinking about this is imagine a surface sort of with some hills. So a point where change won't occur unless disturbed. So if you have a ball or a marble sitting at the bottom of one of these troughs, it's not going anywhere unless there's a disturbance, right? So this is an equilibrium state. And it's a stable equilibrium state because if we were to rock it one way or the other, it would go back and forth a couple times and it'll settle back where it was. So this is sort of we could think of the topography as being sort of some kind of energy, basically. It would take a lot. It would take more energy to push this thing, off in a way that would break the equilibrium, or knock it out of its stable place. So the unstable equilibrium is also pictured here. So it's still equilibrium, because if nothing happens, if nothing perturbs it, it will stay there. But any little disturbance is going to be enough to send it going off in some other direction. So you don't often see this in nature, but it is possible. It does happen occasionally. So the unstable equilibrium could send your system going off into, completely different directions, depending on which way a small disturbance sent it. Could be in sort of stable equilibrium position 1 or position 2. And of course, in reality, these are sort of like multidimensional fields that are hard to visualize. So there's potentials for other equilibriums that could be achieved as well. So we generally see, let's just write that down, we generally see stable equilibriums, or systems in transition. So for a natural system like the climate, it could take decades or centuries for the ball to roll down and fit into another place. Also, generally, a simple negative feedback loop is stable. And generally a simple positive feedback loop is unstable. But there are exceptions to this. And the book gives an example of an exception. But most of the systems that we're dealing with in nature are these rules will hold. Or these sort of, they're not really rules, but this tendency. So for natural systems, generally we have not just a simple 2 or 3 part feedback loop, but we have combinations of positive and negative feedbacks. So really interrelated, sort of webs of many different factors that are interrelated. And determining how these sorts of systems work really requires, to model those requires a lot of computational power in mathematics. Natural systems change in response to what we can call disturbances or forcings. So this disturbance was kind of like back here when I was like, okay, the wind blows and this rock that causes something to happen. It rocks back and forth. A forcing is a sustained. Let's just define forcing. A forcing is a sustained or continuing change. So, for example, when we were talking about Daisy World, so an example of a forcing was we said, okay, over time, this is time, over time the solar flux is going to increase and keep increasing, okay? And the same thing has occurred in the Earth, right? The sun has been getting brighter and brighter over time. So that's not just a disturbance. Like a disturbance would be, okay, you have a solar flare-up, for a relatively short period of time, and the Earth has to, adjust to that. But then it will come back to where it was. The forcing is a more significant, sustained or continuing change. And I'm going to stop there. And the next lecture, we're going to go back into Daisy World and look using some of the things we've talked about here, and get a deeper understanding of how that system works, and hopefully learn some lessons that can be applied to other natural systems.